Alright, so we're going to talk about series circuits today. So you've already worked a little bit with this, and I'll give you an example here in a minute, but with a series circuit, you have, with, with any electronic circuit, you have three different types. You have a series, a parallel, and a combination of both. So we're going to talk about the first one, which is series. Okay. So in a series circuit, only the first and last resistor are connected to your source. This one, we'll talk about why we're specifying that it drops voltage, but that is exactly what it does. Resistors drop voltages proportional to their size and size of the circuit. We'll talk more about that here in a minute. So there's one path for current to flow, and so the current is the same throughout the circuit. So if we go back to our river analogy that has all these dams on it, y'all remember what I'm talking about? So a series circuit is just one riverbed running from the street where it starts all the way down to the ocean. The current is the same. The water does not change its speed in reality, right? It's still moving that same speed. So each dam that is in the way of this water getting to the ocean, each resistor, right? They hold back a certain amount of the push of the river. Does that make sense? So that's what we mean by voltage drop. Each dam you encounter, some of the current will still go through. The water is still moving, right? But it's the force that's moving the water that slows it down, that slows down after it hits the dam. Does that make sense? All right, so looking at this, if your voltage source, you have load 1, 2, 3, and 4. So this would be the spring or the tributary that starts off this river. It goes to dam 1, which is going to hold back some voltage, but let some go through. 2 will hold back more voltage, proportional to his size, so on and so forth, until you get back to source. All right. We won't go deep into parallel circuits right now because that's the next chapter. But just understand that the voltage is applied to each load is the same. They're all connected across the voltage source. The current is distributed in the circuit inversely proportional to each branch's resistance. Like I said, we'll get deeper into that another day. So this is parallel. You have your source, and each load is connected back to the source. It's not really connected to each other. Y'all see that? So each load just connects to the source. They don't connect to each other. The weird thing about parallel circuits versus series circuits, everything's just one big loop. Parallel circuits, that's actually how your house is wired up. So then we have what's called a combination circuit, which is series parallel. So if you look at this, these guys are in series, these guys are in series, but they're parallel to each other. We'll get deeper into that as this term goes on. All right. So resistors connected in series form a string. So the most common example I can think of this is a Christmas tree light strand, which probably is the world's biggest pain in the rear because all of us hate messing with them. Okay. So resistors in series act like Christmas trees, are basically what you use when you string up Christmas lights. Everything's just one after the other in one big row. If one goes out, the whole string goes down. Things like that, right? So these are in series. Well, how do I know they're in series? We go from point A to point B in one single line. Huh? Okay. Not a problem. So yes, resistors in series, you're dealing with something along the lines of a Christmas tree light string, whereby, I guess the best way to say it is nothing ever comes easy. I don't think that's even in the vocabulary of most things. So this guy only has one flow path, and everything is hooked one after the other. So basically, all of these are basic series circuits. So again, these could be a Christmas tree strand light, string of lights, and things like that. But they don't always have to be drawn in a straight line. Matter of fact, most manufacturers, in order to save space and save time, save money, they will not give you a circuit board that's printed out that is perfect. They'll give you something along the lines of C. C and E are two of the most typical formations of this you'll see. Why? Because it's a very compact way of putting 5 resistors in one space, or 4 resistors in one space. There's not as much anything taken up on those than if you what was I about to say? If you're trying to save space, it's the best way to do it. So if I was to connect these in series, there's about 7 or 8 different ways you can do this. You can do something like that. The possibilities are pretty much endless. Because what you're looking to do is just hook them up almost like a train. One, the head caboose, head caboose, head caboose, right? Heads, tail, heads, tail. Same with these. The only difference is that a resistor is not single. They are, can't talk today. The thing about resistors is that they're what we like to call bidirectional. What does that mean? Well, that means that I can put it in either frontways, sideways, backwards, and upside down, and it's not going to affect the component. You have some components, excuse me, just to kind of give you an idea. You have components like LEDs, or what are known as light emitting diodes. These only come on in one direction. Okay, if you put it on the other direction, the light will not open, and the light will not work if you do not have it in the right direction. Does that make sense? So current is the same throughout a whole series circuit. There's only one path for the current to go. And current is all about the flow, right? It's all about going with the flow. So There's a reason I'm emphasizing this, and that's because parallel is just the opposite. In series circuits, you have one path, one current. Parallel, you have multiple paths, multiple currents. Okay? So with series circuits, you have one path for flow. So again, we go back to the river analogy. That's just one riverbed that runs from one place to the other, no tributaries, no offshoots, no anything like that. Does that make sense? So the current does not change in series. You might want to write that down, make a note of it, because that's a great test question, and it's one a lot of people tend to forget. Series circuits, current is always the same. All right, so we start off with 66 volts. We have a red, black, yellow. I'm sorry, black, gold. So it's a 22 ohm resistors, and you've got 3 of them. And what these are telling us, these ammeters, which what do you notice that's different between an ammeter and a voltmeter? It is in series. It's part of the circuit. There's a reason you don't use them a lot in the field. You end up with things like clamp-ons and stuff, which measure the electromagnetic field around conduit, but you rarely actually break a circuit so you can put your ammeter in it. Mainly because then you have to work that circuit live, and if you accidentally cross your leads, you can either damage your meter or you can damage yourself. Make sense? So when it comes to these particular ammeters, they are in series with your circuit. Okay? So the current entering any point in a series circuit is the same as the current leaving that point. Again, just reiterating that. All right, so when we're calculating something like total resistance, the great thing about series circuits is resistance adds. Okay? Simplest way I can tell you right now is that resistance adds. What do I mean by that? Well, I mean that resistors add on to each other. Resistors add on to each other. So the total resistance is completely and utterly contingent upon the resistance in the circuit. Okay. So if I'm going to calculate RT, or my resistance total, I have 56 ohms, 100 ohms, 27, 47, and 10. So what would my RT calculate out to be? It is 240. Why is it 240? Because we added up all our resistance. So total resistance will increase with each resistor added. However, if you take resistors away, what will happen to your total resistance? It'll go down. Now, bearing all that in mind, if I've got a circuit set up with, we'll say, 2 amps of current, okay, And then if I add a resistor, what's going to happen to my 2 amps of current? It's going to go down. Why? Because I'm adding resistance, right? But if I take a resistor out, what will happen to my current? It'll return to normal, or it will increase. Easiest way to say that. Okay. Now, if you have the trick up on the board right now, or on this slide, is the fact that RT is equal to R times N. What that essentially is for is if you have, let's say 20 resistors of the same value. This only works if they're all of the same value. Then you can count up how many resistors they are, what is their numerical value, and then just multiply those together. It's the easiest way I can say that. So Ohm's law and series circuit. Let me go ahead and say this now because this is my biggest thing I harp on with this. And sometimes it feels like nobody ever listens to it, but here goes. Ohm's law and Watt's law that we talked about in intro, they are called laws for a reason. These particular laws don't change. Period, end of. So pay close attention to doing your Ohm's law because it's not changing. We're just adding different factors in. It's still the basic Ohm's law. Current is equal to voltage divided by resistance. Voltage is current times resistance, or current times a specific resistance, which we'll talk about that here in a minute. And resistance is a lot reliant upon voltage and current. Okay? So what we mean by VT, that's voltage total. Anytime you see a little t besides the big letter, all that means is that you've gone from just one circuit where you have one resistor in it to one with multiple. VT is voltage, stands for voltage total. RT is resistance total. Where you see RN or VN or IN, anytime you see the letter, one of those big letters, and then what's out beside it is something like an N, what that is referring to R of whatever the resistance or current or voltage of whatever number resistor it is you're dealing with. Does that make sense? Current of the resistant of that particular resistor, yes. You would find the voltage for it, you would find the resistance for it if you're looking for current at that particular resistor. I'd like to say yes, but a lot of the time what you're going to get, let's see if I can pull, there we go. You get something like this where it's telling you what to solve for. So you're going to end up with things like R1 through R10. Well, I'm referring to a specific number, but since it's the formula for it, I don't have a specific number I'm going to use at that time. So. Alright, so 5 resistors in series. VS stands for voltage source, along with VT, that means voltage total. Alright, so if my voltage is, let's say, 50 volts. First thing I need to know is RT. So what is my resistance total here, guys? Let me tell you the quickest way you can find the answer for this. So 6.5K. Now the whole reason you can find it even quicker is you have a 3K and a 2K, that's 5K. 200 plus 800 would be another K, so that's 6. And then lonesome by himself over here, R2, it's only 500 ohms. So a bit of a quicker way to find that next time, guys. I told y'all back a while back, I do funky math. Mainly because I start trying to look for ways to make it faster. Alright, so I have my VT and I have my RT. What would be my current? So 50 divided by 6,500. So 7 point. So the funny thing about this is that current is constant. So what I can do is now I have my current, I can apply it to each of these resistors. And from there I can find the last element, which is the individual voltage drops. Okay, so what is my voltage at 3.3 R1? Sorry. What is my voltage at 3,000 kiloohms with 7.7 milliamps? $23.1. What about number 2? 3.85. What you said? Number 3. Number 4. And then R5. Alright, so we have found all the elements except for power. Power doesn't change no matter what the equation is. You're going to be doing V times I, as long as you can find V and I. So looking at this, one of the things I can do to check my answer is to add all my voltages up. So in this case, that is 23.1. That is 3.85. 6.16, 1.54, and 15.4. That should get me close to 50 volts, depending on how we round it. You looking for that too?
Yes, ma'am.
On the very bottom,
Okay.
the whole thing. And then you're going to need these. So do we get pretty close to 50 volts here? 50.05. I'll take it. That just has to do with rounding. But y'all see what I'm saying here? This all kind of moves together real easy and works really well, so. All right, I'm going to pause it for just a minute. All right, so let's talk about Kirchhoff's voltage law. Okay, and the voltage law states that the voltage will, the very basic way I can say this is that voltage adds in series. Okay, what it means is that we're going to be taking the voltage and chopping it across all the resistors, but the voltage that goes into the circuit has to come out. Does that make sense? Voltage in equals voltage out. It drops all around the circuit, but it's never gone for good. The other thing I wanted to point out is that power in series adds as well. Well, let me put it to you this way, in a different way. Power will always add. Power company doesn't like it when you try and take away their revenue source. So power always adds. Does that make sense? Okay. So power will always add, voltage will add, and current is constant. All right, so I'm gonna let y'all work this on your own for just a minute. I've got a couple other things I gotta take care of. So work on this list and see what you can find. We'll come back and take care of it here in a second. Alright, so what did y'all get for your resistance total? We'll start with RT. $4 kilo. So what is my IT? Okay, so what can I do with those 30 milliamps? So you take it to all the resistors, so R1 gets 30 milliamps. Okay, so we got the 30 milliamps. So what is my voltage at R1? It should be 30 volts. All right, what about 2? 36. And number 3. Does it make sense to everybody? What about power? Did y'all find that? Total? To 3.6 watts. All right, so dividing that out, what's at R1? 9 what? R2? And number 3. Does that make sense to everybody? All right. So how can I check my work to make sure it's all correct? You add up your voltage totals to check if they match total voltage. And you can also do that with the power as well. That's going to kind of lead you to, is this correct, is this not? All right, here's another one for y'all to practice on a little bit. Alright, so what did we get for RT? You said it was what now? What about IT? Okay. So what do I do now? First of all, you distribute it. Okay. So what is my voltage at R1? Voltage at R1. R2 and R3. Alright, we won't really mess with the power, but you'll kind of get the gist of this now? Alright. So voltages. The interesting thing we can do with DC voltage sources is that we can use them to create a bigger voltage source. When two or more batteries are connected in series, the total voltage is equal to the sum of the individual voltages. What that should mean to you is that if I got one battery that's a 1.5 volt and another battery that's a 1.5 volt, and I put those head to tail, I end up with a total of 3 volts from those batteries. Does that make sense? Okay. Then you also have series opposing, which subtract. So would be series aiding. How do I know? Well, because looking at the sign, that right there means minus, and the long one means I'm going to add. So I've got short, long, which means that those are series aiding. They're bringing your voltage up. Does that make sense? Versus this one. This one is what's called series opposing, meaning they're going to subtract from each other. Another series opposing, because that guy right there is a positive, and so is that. So in other words, you put two heads together, or you put two tails together. Does that make sense? So on this one, we ended up with 36 volts because we added 3 12-volt battery cells together. And this we only ended up with 12 because 2 of them are canceling each other out. That's why if you don't put the batteries into a flashlight the right way, it doesn't work, right? Make sense? Alright, so you can't really see this one very well, but this is 25 volts and 15 volts. First of all, is that series aiding or opposing? So what's my voltage here? Y'all all see how we got that? Okay. What about this one? Series aiding or opposing? Aiding. I know that because this is a negative, this is a positive. So what's my total voltage here? Pretty easy. Okay, so let's talk a little bit about why we do what we do with series circuits. The whole purpose of anything in series is to break the voltage down from one type to another. What does that mean? Well, it means that if I put a big enough resistor in a series circuit with whatever else is on that circuit, that resistor will help regulate the voltage in the circuit. Does that make sense? So that's why we call series circuits voltage dividers, because each resistor likes to take a little bit of that voltage for themselves. Okay? So the basics of this is that the voltage divider is the voltage drop across any resistor or combination of resistors is equal to the ratio of the resistance value to total resistance multiplied by the source voltage. So in this case, they're looking for V1, but they don't have their current, and we're not sure if they've got all the resistors listed. But we want to know what V1 will be with 10 volts applied. So the way it would set up is like this. So you would end up with V1 equals 50 divided by 150. And then multiply that by 10. Running out of space here. So V1 should equal what? 3.33 repeating. Does that make sense? Any question on what a voltage divider is? So troubleshooting, so again, the most common way you see these is in string lights, simply because that's how it's always been done. But what's the bad thing about string lights, guys? One goes out, the whole circuit's toast, right? And sometimes it's just not worth looking through 500 bulbs to find the one that's toast. Exactly. If it's not the fuse that's in the plug, you might as well just go buy a new set, because you're never going to find that one bulb. It becomes a needle in a haystack situation. However, excuse me. However, we can find the missing bulb in a few different ways. So do y'all remember talking about open and closed circuits? What is an open circuit? One that open circuit does not allow for current to flow. What about a closed circuit? One that allows for run. So another couple of terms we're going to be talking about are shorts and short circuits. Neither of these are our friends. Actually kind of dangerous. So a short is where you have an undesirable path for current to flow. Decreases resistance, which increases the total current in the circuit which will cause the total circuit current to increase. It occurs when source conductors and return conductors come in contact with each other, which bypasses the resistance of the loads. And there's several different ways this can happen, guys. Most of it's just through not paying attention or doing something that, while you've done it forever and a day, may not mean that it's the safest thing to do. Okay? Shorts are not a small thing to deal with. Short circuits are even worse. This is where you have no resistance whatsoever in your circuit. Nada. Your power and your current cannot really truly go to infinity, but it can do a dang good job trying. Generally, something gives up and melts before that happens. So, when all the loads in a circuit are bypassed, that's a short circuit. Something's got to give up. Either the voltage source is going to give up, your conductor is going to give up, or your overcurrent protection device, which you really do want to, that's what you want to give up. You want your fuse or your circuit breaker to give up before your house does. That's why you go strictly with what was installed in your house whenever you're buying a new fuse or a new circuit breaker. Because if that overcurrent protection device doesn't trigger, you are going to be in a world of hurt. Does it make sense? We put overcurrent protection devices in these to make sure that they cannot go overboard. And they are known to. So when current flows through minor resistance in electrical conductors, it generates a lot of heat. Matter of fact, if you ever get a FLIR camera and start looking around your house, you can see all the lines where the electrical wire runs because it's a little bit warmer than the wall sometimes. So when metals are heated, the resistance goes up, but the more it becomes a feedback loop. The more resistance it has, the more current is being shoved through, the more it's going to heat up, more it's going to heat up, and it just keeps going through this vicious cycle. And one of two things will happen. Yes, you could very well get a true arc over and cause a lot of problem. Probably two worst case scenarios. First of all, your conductor melts, which creates an open, which is a pain in the butt to find. Not to mention expensive, because you're going to have to tear your house apart trying to find where that wire melted. But the other really bad thing that can happen is you can end up burning down your house. Doesn't take much. Houses have wood, and dry wood is a favorite of fire. So if something doesn't limit or stop that current flow in the circuit, it can melt and cause a fire. We use fuses and circuit breakers to try and prevent that. It's not always successful, but generally it's not because of original equipment failure. What tends to be the cause of that is the failure of the homeowner to understand what they're doing. Like I said, before we went to circuit breakers, a lot of homeowners would just go to the hardware store and get bigger fuses. Well, the fuse won't give up before the wire does at that point. That's one of those things I always try and explain to everybody. You don't want to get something too big because even though it's popping it all the time and that's a little expensive, you might want to start looking at what you can unplug instead of just trying to put in a bigger fuse, which causes more havoc. Of course, almost nobody ever really thinks that that's going to happen to them, but, you know, hey. So fuses and circuit breakers. So the fuse I'm talking about, the one that caused so much trouble is this guy right here. Those used to be installed in every house that ran electricity. Very innocuous looking, isn't it? It's what I like to call the screw-in fuse. So if you ever see an old fuse box, every slot has a screw-in for the fuse. There probably are some other styles out there, but that was very common. So then what you generally will see in things like meters and other electronic devices are these fuses right here. They come in several different ways. Because the interesting thing about fuses is they have all sorts of different functions. So let's say you're trying to start a motor. Well, when that motor first engages, it's going to suck up a lot of current trying to jump itself. Does that make sense? So you don't want something like a fast blow fuse in that. You want something that will understand what's going on. So you have what are called fast blow fuses. Those are typically in your meter and a lot of other electronics. What those are meant to do is what? Break when a surge happens. Try and protect your device. Make sense? Then you have time delay fuses. You have all sorts of these things. Time delays are, like I said, those are used with things like motors. Why we use them with motors? Well, because I'm going to be for about 5 seconds pulling excessive current through this thing so that I can get my motor turning. Get that motor to turn over, right? So we use time delay fuses with those. And then you've also got your basic circuit breakers. You know where your circuit breaker is, guys? You ever had to go down and flip a circuit breaker? Yeah, it's a little bit back there and it's kind of a pain to get through, right? But there's a reason for that. Most homeowners don't want to get into their circuit breaker panel. It's probably a good idea too because it keeps them out of trouble. And if you notice, these things actually screw in are clipped and screwed and everything else to whenever they're put in. Just makes it a little bit harder for whoever's working on it. If they're not a professional and know exactly how to get that off, they don't need to know how to get it off. Especially on some newer places like new builds, electricians try to make it to where the homeowner can't get to it because otherwise, liability tends to be the name of the game a lot of these days. No, it's more of a homeowner decided they wanted a bigger breaker, but the rest of the house isn't rated for that. So they go in and put it in and burn their house down, and they try and blame it on the electrician. So you make it harder for them to do something like that and pull those kind of stunts. You stay in business longer. You keep the customer safe, you stay in business better, and the world's a better place for it. Because when you're in any kind of a trade like that, you yourself are held liable for any and all damages to property and everything else should something happen as to the terms of your work. So let's say you're a really crappy electrician, you've got junction boxes everywhere, and you got them stuffed with, let's say, newspaper. Well, you're not very bright, are you? But, no, I'm not. Huh? Yeah, the circuit will be what catches fire. So if you're the electrician, that's your fault. However, if I'm the homeowner and you just left my house because you were done with your job, but I decide I want to go put in a pot light, how hard can it be? Wire it up, put a junction box in and everything, and I'm the one that put the newspaper in there. my house burns down, I'm not going to tell the insurance company it's my fault. Tell it's your fault. You're the electrician. That's a lot of what happens. So with things like circuit breakers and a lot of this other stuff, uh, people have kind of gotten smart and wise to what happens with that. So a lot of the time they're trying to make sure people can't just randomly go in and do something they don't know what they're doing. You know what I mean? There are some companies that even put stickers across where the two parts of the circuit breaker cabinet meet along that seam on the edge. They put that there so that the homeowner has to break that seal in order to mess with that circuit breaker. At which point, that's what do you want me to do about it? It happens more often than you think. So with a short, we're looking at things that take a path we don't want them to take. So if, say, a resistor has no resistance whatsoever, any and all resistance has been burned out of this thing, then that's a short. Okay? That can happen across any load. A short circuit means that your wire 1 and your wire 2 are now in contact with each other. This is where bad stuff will happen. Okay? This is where bad stuff happens very frequently. Because now your circuit is constantly giving itself feedback, and that feedback loop is going to cause a major issue. One of the coolest things and the most dangerous things I've seen is where somebody takes something like a 9-volt battery, puts a gum wrapper across it, and is able to start a fire. Because basically what you've done, since that wrapper has just a little bit of metal to it, you basically used it to create a circuit without a resistor. Not a good idea. Really, it's not. All right, so insulators. To prevent shorts and short circuits, we take conductors and isolate them from themselves. This is why every time you look at any kind of a cord or cable, if you look inside them, with the really big ones, they have bundles of cable. But I digress. So we try and keep source conductors away from each other. Source and returns should never come in contact. If they're even touching each other, they need to have a bunch of insulation between the two so you don't end up with arc over. So insulators are made of things that exhibit extremely high opposition to the flow of current and protect the conductor against the environment. A really good one is sand, believe it or not. Sand goes into making glass and everything else. So that's actually generally a good insulator. We tend to think of rubber first and foremost, but it's not the best of the best. All right, so insulators, that's what's wrapped around these wires. This is a printed circuit board, which these little lighter lines like this are what are called traces. Now, the bad thing about traces is if you're dealing with them, you don't want to damage them. It's kind of hard to get into the green board and repair anything like that. And then we use air as an insulator. That's what these lines are doing. These are transmission lines. They're transmitting from one part of the power company all the way to your house. In doing so, we don't want those coming in contact, and you could call it a big boom. I mean, that's not going to be good. So they use air to isolate them. Because the bad thing about transmitting electricity is what? Huh? Well, you're not so worried so much about arcing. It's you can't have excessive weight on this because the more it weighs, the harder it is to put it up and down. A, B, the harder it is going to be to service, and C, the more problems you're going to have otherwise, drooping and things like that. So they keep this as light as possible. It's why they use aluminum as their wire of choice to get the transmission lines up. Aluminum's light, it's a semiconductor, and it's cheap. But they don't want to insulate it because then you're going to add weight to it. With these transmission lines, what you're looking to do is to get the electricity from one place to another. And if you added insulation to it, you might actually cause some other problems I'm not going to get into. Alright, so before we get into opens, I'm going to give y'all another 10-minute break to get up and kind of move around. So we've already talked about a short. That is where the very basic term of a short is the fact that it pulls excessive current. Okay? A short is all about having excessive current flowing through it. So an open is the exact opposite of a short. So if a short has excessive current, what do you think an open has? Very little to no current. As a matter of fact, it has too much resistance. Okay? So it allows no current to flow through the load. So it prevents current flow through the entire circuit. So you have an on-off switch, which is deliberate, fuses and circuit breakers, if you had too much current going. And then just faulty connections are some of the biggest causes of that. All right, so in a series circuit, all opens create an open circuit. Okay, and there's a reason I'm saying that's for a series circuit only. So an open circuit means that nothing's coming on. Okay? All right. So how do we find an open? So in a series circuit, this is one of the most common ones. They can't be detected visually all the time because we can't always see what's going on inside the wire. Total resistance is infinite, which means you've disconnected it from the power source. Total current is 0. When tested with a voltmeter, the total voltage measures across the open. Okay. So what you're looking at here is how do I find, let's say we do have that Christmas tree strand of lights and we want to find out where the bulb has burned out. It's created an open, right? Load is no longer there. So what you're going to do, you can't detect it visually because guess what? The whole string's down, right? So we know that the resistance will be, total resistance will go to infinity because there's just too much resistance there. There's no current going. So when we start using a voltmeter, you start looking for where is the voltage sitting. So let's think about an open as, if you've ever seen the big bridges that have the ability to open, and close depending upon if there's a boat that needs to enter the harbor or not. When a bridge like that is open, where's all the cars? Where's all the traffic flow? It's waiting here at the back end of it, right? Because the cars can't go up over that gap. They're waiting for it to close. So the same thing happens with voltage and current with these circuits, is it's all waiting at that open for that bridge to close. Does that make sense? So we have all the cars back here. We have all the cars back here. So with an open, when you put your meter here and here, you'll read your total voltage. If you read it anywhere else, there's no voltage or current there because it's all sitting where? Sitting at the open. And it's kind of like when a train gets in the middle of the road. Well, you can either have to try and find a way to turn around, or you just sit there and wait for it to move. Make sense? So checking for and identifying shorts. These occur when two conductors touch. When you test a short with a voltmeter, it won't measure any voltage. Why? So let me ask you this. Why do we never see voltage drop across a fuse? Or across a piece of wire? A little bit different than that. What's going on is the fact that they have no resistance. If you have no resistance, you have nothing for it to stop at. So let me put it a different way. Going back to the river analogy with our water flowing from the top of the mountain down to the ocean, right? If there's no dam there to do the work, let's say the dam busted and everything flew downstream, and there's nothing to now gather behind it, right? That would be a short. Does it make sense? So an open would be if you dammed up the whole thing and made it to where water could no longer flow down it. A short would be if the dam breaks and all the water is just rushing through it. There's no way to stop it. So opens can be a big deal because if we're going with the dam analogy, you have the fact that the people downstream are going to be dry as a bone. You might have problems downstream because the water's all stuck upstream. Does that make sense? If you have a short, you're going to definitely have problems downstream because all that water is bypassing that one dam and it's heading downstream for whatever's there. You could end up with quite a wall of water that just wipes everything out downstream. Does that make kind of sense to y'all? All right, so some key terms here you need to know for our first test, which we'll be going over a few other things before we get there. I'll let y'all write those down for those of you that want it. In the meantime, let's see if I got what I need here. Alright, so what I'm going to hand y'all now, in just a minute, we're going to take a look.